Okay, now we come to the magnetic circuit, right? And then we talk about the electrical mechanical energy conversion. Right? But mainly, I will focus on the magnetic circuit. So, and from the transformer part, we talk about that. It will be included in the next course. Electrical engineering 2, right? For the student, those who need to take the electrical engineering 2, you will learn about transformer, motor, generator, power electronic, okay, and control system. So a lot, right? Sorry about that. Okay, okay, let's talk about the electricity and magnetism. Okay. This is another type of circuit, right? So far we have learned about many types of circuit, including transient, right? And then what? Diode, right? Diode and with BJT, right? And bijunction transistor, right? And then we also have op-amp, right? Op-amp. And we then have digital circuit, right? Digital logic circuit, and this part will be the magnetic circuit, right? It's totally different. And this part we will have the idea about the energy conversion mechanism. We convert the energy between electricity and magnetic. Okay. Well, so far that you have learned in the physics course, right? We know about the phenomena about electricity and magnetics, right? Behavior, right? There is some interconnected together, right? If you have electric field, you will have magnetic field, right? At the same time, right? We call electromagnetic phenomena, right? And then the researcher found that the electric current produced magnetic effect here, right? By the Danish physicist, right? And then after that, Ampere found that there is a relation between I and H, right? We mean the Ampere law. So we will discuss about what is Ampere laws. And then the researcher found also that the magnetic field can generate electric field. If we move the magnetic field, we can generate electricity, right? By moving magnetic field. Okay. Okay. Or we can state that the Ampere law state that a changing magnetic field give rise to voltage. Right? If we have the magnetic field is changed during the time, if we change the magnetic field, if this is the magnetic flux, if the flux of the magnetic is changed, this will produce the voltage. Okay, you get the voltage. If the flux is constant, there's no voltage there. Okay, if you just take the magnetic and we didn't move it, right? There's no current, no voltage. Okay, but if we move the voltage will be ampere. Okay, you know that, right? You have learned about this, right? Okay. So then the quantity used to quantify the strength of the magnetic field, right? If you talk about the magnetic, okay, the parameter known as magnetic flux, right? Yeah, it's the flux of the magnetic. Is this unit in Weber? Okay. The number of flux, right? And then if we talk about how density they are, we use the capital B, right? Stand for the magnetic flux density is B. So it's the Weber per square meter. So if we have the area of A, and this is the magnetic flux, total flux, the density, total flux in Weber, and A in square meter, right? The density, therefore, the density is the flux per area, right? It's the Weber per square meter. Okay. And also we define the magnetic field intensity, right? Intensity in ampere per meter, or H. So H is depend on B. B and H are related together. Okay. So later I will talk about B is mu into H. It's depending on the permeability of the medium. Okay. Yeah. Okay, the magnetic field can be generated by electric charge in motion, right? And the effect is measured by the force they exert on moving the charge. If you're moving the charge, right? And the vector force, or F, exerted on the charge Q moving. If we move the charge, right, in this direction, under the magnetic field here, we get a force here, right? Force that we obtain here. Or F equal to Q in this direction, right? Cross the field, right? The magnetic flux density B. This is the how do you call this law? This is the right hand rule, right? Or left hand rule, right? Right hand rule, right? We cross in this direction, right? We get this force, right? It's the right hand rule, right? This force will be in this direction, right? Right hand rule. Right? Oh, this is the QUB sine theta, right? And in this direction, cross in this direction. And cross in this, and we get the force in this direction. Okay. And in reverse, the flux is the integrate of Weber per square meter, right? Weber per square meter integrate is flux. dA, right? dA is area, right? This is area. Yeah. Okay, flux is Weber. Or if we have uniformity of the magnetic flux, so the magnetic flux is equal to B into A, right? This is B into A. B is flux per area, right? Total flux would be the flux per area multiplied with the area, right? If this is uniform, right? If it's non-uniform, you need to do integration, right? You need to integration, okay? Just as a symbol for physics of magnetic theory, right? And then if we talk about the Faraday laws, right? Faraday law states that if the imaginary surface A will bonded with conductor, then a charging magnetic field would induce a voltage. Okay. So E is d phi by dt. If the flux is changed, if you have the flux, so for example, if you have the coil like this, and if you have one magnetic, right? If this this magnetic field is not changed, if it just stays steady, there is no voltage there. But if we move if we move this magnetic field, you will get the voltage, okay, we generate. So the relation is d phi by dt. Yeah. Is the, we call this is a magnetomotive force. Right? We will get the electric force as the voltage, right? Or voltage, or d phi by dt. Yeah. Okay. In this is negative. Yeah. So if we move the magnetic density or magnetic field, so we get the voltage here. Right? And if this is a closed circuit, the current will be there. We get the current there. Okay. Here. Okay. Under the right hand rule here. Also, if for example, if you have the magnetic in this direction, change in this direction, the current will be in this direction. Okay. Oh no, its current will be in this direction. On the right hand rule, okay. Or if we supply the current in this direction, the magnetic field will be in this direction also. Okay, the relation will be in compliance with the right hand rule also. Okay, you learn about this, right? You have learned about this. So I will go. This part will be go a little bit fast, okay? But we will have time to talk about the magnetic circuit. Okay. Okay. Commonly we neglect the minus signs. Okay. We consider about the amount, right? Yeah. The absolute value of voltage. Yeah. Then if we have magnetic flux cross many turn of coil, the number of coil would be here, n turn of coil, right? Because the total flux or lambda will equal to n into flux, right? This is flux per turn. This is total flux. Here, okay. Here, flux, total flux is equal to n into flux per turn, right? This number of turn of the coil here, right? Then E equal to d lambda by dt, or n d phi by dt here, okay? N d phi by dt. We already know that I is dq by dt, and lambda is Li, and the volt is Ldi by dt, right? Yeah. So if you have the conductor coil, the voltage will be if you change the voltage, you will get the change in flux. Vi, if Vi is changed, you get the flux is changed, right? For example, if Vi is alternating voltage, like it's AC voltage, when you coupling this coil with another coil, and if the flux is induced to another side, Vi is d phi by dt is the, sorry, it should be n1, right? It's n1 d flux by dt, right? And then on another side, it will be induced by n2 d flux 1 by dt. It will produce V2, right? And these two are the same. Then you will get that the relation between V1 and V2 is equal to N divided by dt, and N divided by dt is equal together. Then V1 by V2 equal to N1 by N2. This is the basics transformer theory, right? This is transformer. We can build the transformer by this theory, right? We can convert the voltage with this theory. It's a magnetic field theory. Okay. Okay. Then now, if we consider about the energy stored in the magnetic field here, we just integrate EI. And E, what is E? E is d lambda by dt, right? d n divided by dt, right? Or we can have I and d lambda. If lambda is changed here, right? It's I into total flux minus WF here. This is what constant, right? And we can have that the energy conversion, and we have another side is the core energy. We can core energy. Okay. And we can have the relation between flux linkage and current and energy, and then core energy. Okay, now I talk about Ampere laws, right? So Ampere law states that the magnetic field intensity, or H, in the vicinity of conductor is related to the current carried by the conductor, and the relation between the magnetic density and intensity is depending on the medium, right? It's dependent on the permeability of the common material. So if the magnetic field pass through different material, you will have different permeability. Okay, the intensity is depend on the density, right? It's a force, and it's depending on the medium that the magnetic field pass through. If it's passed through the air, you get mu at 4 pi multiplied with 10 power minus 7. Okay. For the free space or the air, right? Mu of free space is 4 pi multiplied minus 7. Okay. So the relation is B equal to mu H. Okay, mu H. M is the magnetic field is conducted by thermoid. The permeability will be very high. It's very high. It means that it tend to pass to this. It's easier, right? It's easier to pass to this type of material. Okay, if the magnetic field pass to the air, it will be very low value, right? But it's passed to some medium like steel, metal, or iron, right? It's easier to that the magnetic field pass to this type of material, right? Because the permeability is higher. Permeability is similar to the conductivity of electricity, right? And this is the conductivity for magnetic field, okay? The conductivity of magnetic field. This is the conductivity of magnetic field. Okay. Then usually we define the permeability. We show the permeability in terms of mu zero, in the term of free space permeability. If the free space permeability is mu zero, right? If we use sheet steel, for example, we use sheet steel, it will be 4,000 into 4 pi multiplied 10 power minus 7, right? This is mu equal mu r, and this is mu o, right? Like this. So we use mu r. We indicate in mu r is easier, right? So in how many times of the permeability, right, of that material, right, over free space, right, over free space. So this is the relation between B and H. And B is the unit of B is Weber per square meter. Yeah. Or Tesla. Tesla. Okay, now we have this relation, right? Okay. And this is for free space here. Okay. And we can use relative permeability to represent, right? Relative permeability to represent different type of material, right? Of material. Okay. And also then when we talk about the Ampere laws, right? The magnetic field intensity is related to the current, right, of flow in the conductor here, right, the conducting wire. So the relation is we have the closed path integral of H dl is the range, right, of the part is equal to the total current, right, in that closed loop part here. Or if we solve this, we will get H equal to I divided by 2 pi r, because we integrate closed path in the circle. This will be 2 pi r H, right, equal to I. Therefore, H is I divided by 2 pi r. What is the range? The range of the magnetic part in closed loop here. The range of magnetic part in closed loop. This is L, right, here. Then with the given magnetic field intensity H will give rise to different flux density. Then we define one very useful term as source of magnetic energy. We call electromotive force, or MMF. Okay, if the magnetic field is there, we will get electromotive force, right, and can be calculated by F equal to Ni, this number of turn and ampere here. This we call electromotive force. If you have the current flow into N turn, the force to drive the magnetic field F equal to N into I. Okay. This is the unit, therefore, ampere turn, right? Ampere and turn. Okay. And then B equal to mu, B equal to mu H. Okay. And for the flux density of tiny valve circular coil here, L is B. H is what? H is Ni divided by L here. Therefore, B is mu H is mu Ni divided by L. And for the toroid here, we have H is 2 pi r, right? L is 2 pi r2, right? This is L. It's mu Ni divided by L also. Okay. So in conclusion, the magnetic variable and unit can be shown in this table, right? So we have current is I, magnetic flux density is B, magnetic flux is phi, right? That's B is phi divided by A, right? The magnetic field intensity is H, so B is equal to mu H. It's depending on the permeability of the material, right? And we have also electromotive force E. E is depending on the change of flux, right? Of total flux during the time. And then electromotive force or Therefore, this is F, right? So we can have this relation. B is mu F divided by L. Then F is then BL by mu, just like this. So if we consider the magnetic circuit now, we come to magnetic circuit. If we force the magnetic field to the specific material, so this material will have high permeability, right? If you just have the air material, mu will be 4 pi into 10 power minus 7, right? But if you cross this coil with the high permeability material, it will be easier for the magnetic field to flow, right? Okay. This will be called a magnetic circuit. Yeah. So the flux is easier to go this path. So if you have the magnetic field in the air, it will be flow like this, right? You have the closed circuit, right? This can lead into many ways. In fact, in this case, you also have the leakage flux also. The leakage flux will be there. Okay, but for the if you use high permeability, high conductivity, right? The magnetic flux tend to flow in this material rather than leak to the air. Okay, that's we can control the magnetic to flow in this direction to the core, right? Because this is the core. So this type of material we use in we control the flux into the different direction, and we can build transformer. We can build the motor or the generator, right? So then this kind of equipment will have the structure with the type of material, high permeability material. Okay. So if we get another turn, another coil in different paths, we can control the flux to cross to another coil, right? Another coil. So this is a simple transformer circuit, right? Yeah. So the relation between V1 and V2, therefore, V1 by V2 N1 by N2, like this. Okay. Okay. From the relation we know so far, B is flux per area, right? This is Weber per square meter. And H is B divided by permeability, right? It's therefore B is flux per area. Right? B is flux per area. We substitute here. Right? And the magnetomotive force is N into I or H into L. Right? Therefore, we substitute H. We substitute H here, right? The magnetomotive force then flux with L divided by mu A. So flux. Oh no, into L by mu A, right? Okay. F is flux into L by mu A. This is similar to V equal to IR in Ohm laws, right? This is L divided by mu A. We call this is the reluctance. of the circuit. Okay, reluctant circuit. When you calculate R, what is R? It's rho L by A, right? R of the material is rho L divided by A. You remember this, right? Or is L by conductivity into the area, right? For the resistance, when you calculate the resistance, is depending on resistivity and conductivity, right? And conductivity. And similarly, L divided by mu A, right? Mu is conductivity for magnetic circuit. So mu is similar to conductivity of the magnetic circuit. This is for electricity. This is for magnetic. Right? This force is just similar to volt, right? And the flux is similar to current, right? The flux is flowing, right, to the medium material. Okay. So we can use this R, right? Eclectic R, right, for the reluctance, right? L divided by mu A is we call the reluctance of the magnetic circuit. Then we can calculate this type of circuit similarly to Ohm's laws. Okay, similarly to resistive circuit. Okay. Okay. In conclusion, if magnetic field intensity is electric field intensity, right, is similarly to magnetic field intensity, right? And the voltage is the magnetomotive force, right? Yeah. The current is the flux. Yeah. So if you have this circuit V and then what is V is I into R, right? And for magnetic circuit, the magnetomotive force is F, right? This is magnetomotive force. And the flow is the flux, right? Okay. F is flux into the reluctance of the circuit. Okay. Similarly, flux is similar to I, F similar to V, right? And R is reluctant like this. Okay. Or we can calculate the reluctance by L divided by mu A, right? And mu of the material is relative permeability into of the permeability of the free space. Yeah. So if we know the cross-sectional area, this is A, right? A is the cross-sectional area, right? A, yeah. A, right? And L is the range of the path that the flux flows through, right? L. So if we know the number of turns, we know the current that we produce, the flux, we will get F, right? We'll get the magnetomotive force in ampere turn, right? In ampere turn. So what is F? F would be N into I. So this is I, right? So if we supply the current as I ampere into the N turn of a coil, we can get magnetomotive force as this ampere turn, right? Ampere turn. And then we can calculate the reluctance of the core. The reluctance can be calculated by L divided by mu A, right? Sorry, this is not equal, right? This is multiplied. L into L divided by mu A. Okay. Here, this is an example, right? If we have N of turn of the coil and we supply I, what is F? Magnetomotive force is N into I, right? And what is the reluctance of this? Okay. So if this part of the core have the area of A1 and this part of the core have the area of A2, right? So the reluctance of different parts is different, right? But in series circuit, you can get this. So for the upper part of the core, this is the reluctance is R1, and if the same for the lower part, it also have R1, and on the right hand side is R2, and this is also R2, right? The circuit will be magnetomotive force into R1 and R1, right? R2 and R2, right? This is the left part like this. You can construct the equivalent circuit like this. This is the reluctance R2. This is reluctance R2. Reluctance of R1 and reluctance of R1 like this, right? And the flow is flux flow, right? This is an analog circuit representation, right? Like this. Okay. And R1 can be calculated by L1, right? L1. Sorry, I used to flip. This should be A2, right? R1. This should be A2, and this is A2, this is A1, this is A1, right? And this is R2, R2, this is R1, right? R1, and this is also R1. So for R1 will be L1, this range, right? This range is L1 divided by permeability with A1, right? A1 is cross-section area of this part, right? Similarly, R2 would be L2 divided by mu into A2, right? This is cross-section area, okay, here and here. And then we can calculate the reluctance, and we can calculate how much for the flux, right? So if we have F will be flux into total R. Therefore, total R is R series, right? R series here, right? We know R and we know F. We know how much the flux now. Okay, we can calculate how much for the flux now. Okay. I think we can continue, right? Continue, no breaks. You don't need break, right? Okay. So let's see this example. Okay. So we can calculate the flux density and field intensity on this magnetic structure. Okay. Can you do this? So L is 0.1 meter, or how much for 0.1 meter? 10 centimeter, right? Right? 10 centimeter, right? We have this draw. And H also 10 centimeter. And this Y is just 1 millimeter, right? Right? 1 centimeter. 1 centimeter, for example, right? But we use the unit of meter is our calculation, right? So if this is 0.1 and H is also 0.1, right? And the inner range is 0.8. So the mean part will be 0.09 here. Okay? The range will be 0.09. And then H is also similar, right? Here is also 0.1. So this is also 0.09 for this part, right? So total range will be 0.09 plus 0.09 plus 0.09 plus 0.09 for magnetic part, right? Here, right? So let's see. In this case, the material have the relative permeability of 1000. The number of turns is 500 and the current is 0.1 ampere. The cross-section area would be W square, right? This is W. The cross-section area here. This is 0.01, 0.01, right? And this is also 0.01, right? Right? And this is 0.01, right? This side. How much for the cross-section area? 0.01 square, right? Is 0.001 square meter. Here. Okay. So our assumption is all magnetic flux is linked by the coil, and the flux is conducted by the magnetic coil. The flux density is uniform, right? So no leakage flux. All magnetic flux is into the coil. There's no leakage flux like this. Okay, this is our assumption. But in practice, there is some small leakage flux, right? Okay. So we neglect the leakage flux. Okay. Then we calculate the magnetomotive force, and we get 500 turns into 0.1 ampere. This is 500 turns, right? So magnetomotive force is 500 into 0.1. How much? It's 50, right? Ampere turn, right? It's 50 ampere turn here. And then we calculate the mean part is 4 into 0.09. This is the range L, right? So in this case, all parts are equal, right? For this 4 part, right? We get the same reluctance, right? For this 4, so then we can calculate one reluctance, right? For this magnetic part. Okay. So the reluctance will be L divided by mu A, right? L. How much for L? L would be 0.36, right? 36. And A is 0.00001, right? Okay. And mu is 1000, right? Mu is 1000 into 4 pi e 10 power minus 7, right? Okay, here we have all required parameter, right? R is L divided by mu A, right? So this would be 0.36 by 0.00001 1000 4 pi minus 7, right? So I just here. A, this is A. Okay. Then we get 2.865 multiplied with 10 power 6 ampere turn Weber. This is the reluctance here, right? Okay. And then we have 50 ampere turn. Right now we can calculate how much for the front. Okay? So we get the total flux of 1.75 multiplied with 10 power minus 5 Weber. We get flux, right? And how much for the flux density? Flux density is the flux per area, right? And flux per area will be 1.75 multiplied with 10 power minus 5 divided by the area. The area is 0.0001, right? Then we get this flux density. And also we can calculate magnetic field intensity. Intensity will be H is B divided by mu, right? Because B equal to mu into H, like this. So we get this intensity. It's all the equation, right? Total flux, right? Flux density and field intensity, right? We can calculate with this equation, right? With this problem. Okay, an equation. Okay. Okay, then if we have some more complicated circuit like this, how to calculate the magnetic circuit? Okay. With this. This is, I would like you to try by yourself, right? But the circuit will be like this, right? You will have the reluctance of this path, right? 1, here, reluctance 1, like this. And then this path, this path, this path, this path. It's just like the resistive circuit. So we can calculate the reluctance of each part, right? Of each part by mu L divided by mu A, right? It's not so difficult, right? But it's so many things to do, right? Part by part, like this. Okay. So I would like you to try this by yourself, okay? Can you do it? It's not a homework, but it's a practice, okay? So this depth also 1 centimeter. So you get the mean part first. Right? This is the mean part for the range. L. Here. L is 5 centimeter. L is 5 centimeter. This is 2 centimeter, right? This is 5. Like this. This is 5, right? This is 2, right? This is 1. And so the magnetic part would be, this is 5 also. This is 5 also. This from this to this. This is the mean part, right? You need to get the mean part for calculation, right? Here, right? So how much for this range? So I use L1 here. How much for this range? This is 5 and this plus 1 and plus 1, right? It's become 7. Yeah. And how much for this range? This is 5 and it's minus 0.5 and minus 0.5, right? And it's become 4, right? Very good. 4 is not. This is 4. If you calculate the reluctance of this part, is you use L equal to 7, right? And A is equal to, A will be 1 centimeter, right? With the depth of 1 centimeter, right? Right? Yeah. 1 by 1, right? 1 by 1. So in the unit of centimeter, of meter, 7 by minus 2, right? Yeah. And A would be 1 minus 2 into 1 power minus 10 power minus 2, right here, square. Okay, here this is L and A is there. You can get all reluctance, right? And once you get this reluctance, so you may sum these three reluctance together, right? These three reluctance together into one, right? And then this is, you can use parallel circuit, right? You use parallel. You sum this reluctance in parallel, right? Just like you calculate the total resistance of parallel resistor. Okay, similar to parallel resistor. Then you sum three together. You should get equivalent reluctance at this value. Okay, just try to check it. So if you can calculate, it's all reluctance, okay, and then finally you get the total equivalent reluctance of this value. Okay, it's okay for you, right? Maybe this evening you try it on this evening. Okay. Then in many types of magnetic circuit, we have the gap. Okay, the gap we call air gap. We call air gap. The gap is there, and the gap will have a very much different permeability. This is mu 0, right? And this is mu r into mu 0, right? For example, in the complicated magnetic circuit like motor, right? If we have the motor, the rotor is here, and this is stator. The gap is here, right? We get the gap when the magnetics cross this gap. Okay? This type of circuit, when we have the gap in our circuit, right? Okay. So how to analyze when the magnetic circuit have the air gap, right? So this we have air gap for small gap. Small gap, but it will be very high reluctance. Very high reluctance. We can see that if we have this type of circuit, our circuit will be with this form, right? This is the magnetomotive force, and this is R1. This is R1. This is R2. This is R3. This is R4. And this is R5. And this is RG. Right? R of the gap here. So if you substitute the reluctant formula, R1 will be L1 divided by mu R, mu O and A, right? This is R1. Here. R2, R3, R4, R5. Okay. And RG this is the range of the gap. Okay, it's L, right? The range of the gap is lambda. It's very small. This value is very small if we have small gap, right? And divided by mu O. Mu O is also very small, right? This is 4 pi divided by minus over 10. And the air gap is also small. Therefore, RG will be high, right? RG will be very high. So if we use the high permeability material to build this type of magnetic circuit, what happened? R1, R2, R3, R4, R5 will be very low. Very low. So if you use high permeability, like this, this is high value, this is high value, this is high value, this is high value. So R1 is low, RG is high, right? Okay? Approximately, we can almost neglect this part. And we will have only RG in our circuit, right? It's become easier, right? Just become easier, right? If you use permalloy, right? If you use permalloy as our material, so R1, R2 until R5 is very low value, right? It's negligible, right? It's negligible in the calculation. So better to have the gap in the circuit, right? No? Okay. Okay. So let's see this example. If you have this bottom plate, right here and here, of this circuit. So the depth is 0.01. So this is 0.01 also. Okay. So in this case, so I will skip some detail, right, of this example. I think you can go into detail here, right? For this part, here the magnetomotive force will be Ni. So in this case, N is 100 turn and the current is 1 ampere, is 100 ampere turn. Okay, and the part will be IC will be L1 to T2 air gap, 2 air gap, right? This is air, the range of the air gap. LG, we have 2 LG like this. Okay. So if we break into T-legs like this, so LU is the U part, right? We have U part 1, 2, 3, and the bar is here, range here, and the range of the gap, we have 2 gaps like this, right? Range of the gap here is 0.05, U shape and the bar shape. This is to break into 2 parts. So the area of the gap is 0.1 plus Lg squared, right? Here. This is the area of the gap here. The depth is 0.01, right? 0.01 and 0.01. In this case, they also consider the frinking. Why we have Lg here? The area of the gap should be 0.01 by 0.01, but if we consider the frinking flux means here, the area may be greater than the area of the gap. The A of the gap may be greater than the area of the core. Okay, if we consider frinking from here, but usually we can neglect and we can use the same area. Okay. Okay, but in this case we have the area of the gap like this square here. Okay, a little bit more detail, right, when we consider the frinking flap here. So the reluctance of the U shape is 1.43 into 10 power 5, and the reluctance of the bar shape here, the lower part, we get 0.715 into 10 power 5. Okay, here. And for the air gap, even they have the very low range here, the magnetic part of air gap is just only 0.005, but the permeability is very low here, right? Then we get 3.98 multiplied 10 power 7. You can see this is 10 power 5 and this is 10 power 7, right? Okay, it's 3, 4, 3, 9, 8, 1, 2, 3, 4, 5, 6, 7, right? But for this is 1, 4, 3, 1, 2, 3, 4, 5, right? It's much different, right? It's much different. And this is 7, 1, 5, 1, 2, 3, 4, 5, right? That's only this value. So we can consider most is come to the air gap, right? The reluctance affect the circuit is from the air gap, mainly from the air gap. So the total reluctance will be these three terms add together. You can see that it's just similarly to the air gap, right? This is mistyping. 2.55 is mistyping, right? Right, it should be 3.98, right? And it's almost equal to 3.98. So if we neglect the reluctance of the core, right? The core material, we neglect reluctance of core material, we can calculate the total reluctance just from the air gap, right? Just from the air gap here. Sorry. So this is very common to neglect the reluctance of the magnetic material, okay, in approximate calculation, okay. But this may not be in the examination with air gap, right? Okay, this is if we neglect the reluctance of the material, we can get more simple circuit, right? Like this circuit, we can just consider only the reluctance of the air gap. It's affect mostly to the circuit, okay? Yeah. This all to your final exam. Try to do this homework, right? Okay. I think it's not difficult, right? So I didn't solve this homework for you. It's not difficult. If I solve all, it's just become the example, right? It's not homework anymore. So I solve only some question for you, right? Just some question. You try to do by yourself. It's better, right? Maybe it takes time, but it's very good for you. Okay. I think this is not difficult, right? can do this. See this circuit. It's okay. Any question so far? This is mu is 3000, right? What is this circuit? You get this and this reluctant and this reluctant and then this reluctant and then this reluctant, right? And then this reluctant, right? So you need to calculate the part, right? The mean part of this circuit. This is R1. R1 would be L1 by mu A1 by this, right? Yeah. And the parameter is there. Okay. And then the question also asks if you have the gap for 0.1 at L3 like this, if you have this gap, what happens, right? I think in this question we can neglect this value because this is very short part, right? We have no parameter on this. We have only L1, L2, L3. Right? This part, I think we neglect this. Okay? In the calculation. Right? And for this question is the transformer, right? Transformer. Relation of the transformer. If you have transformer like this is 220 and this is 20 volt, and the low voltage side we have 50 turn. It means that this side we have 50 turn. How much for N1? Okay, it's not difficult, right? To do this 13.20 and 13.21. Okay. So you have another one homework. It's the final homework. Then see you on Tuesday morning, right? Okay. Ready? You're ready for final exam.